Imagine a time when our universe was an infinitesimally small point of unimaginable density and heat. This was the singularity, the seed of everything we know. In a cosmic instant, this singularity began to expand outward in a cataclysmic event we call the Big Bang. The Big Bang wasn't an explosion like a firework. It was the rapid expansion of space itself. As this expansion continued, the universe cooled, allowing energy to transform into the building blocks of matter. The universe, in its infancy, was a chaotic and unimaginably hot place. Temperatures were so extreme that matter as we know it couldn't exist. Instead, energy reigned supreme, governed by the laws of quantum mechanics. It's within this quantum realm that the seeds of our universe were sown. The Big Bang remains one of the most profound concepts in all of science, a testament to human curiosity. In the first moments after the Big Bang, the universe was an inferno of unimaginable heat and energy. Yet, as the universe expanded, it also cooled. This cooling set the stage for the creation of everything we see around us. Imagine a kettle brought to a rolling boil, steam escaping and transforming into tiny droplets of water. Similarly, the universe underwent a series of phase transitions, much like water transitioning from steam to liquid to ice. These transitions were crucial for the formation of matter. As the universe cooled, energy began to condense into matter, guided by Einstein's equation, E equals mc squared. In the early universe, energy coalesced into particles of matter and antimatter, twins locked in a cosmic dance. However, a slight asymmetry in the laws of physics favored the survival of matter over antimatter. This tiny imbalance is the reason our universe is filled with matter and not just a sea of radiation. As the universe expanded and cooled, the stage was set for the emergence of the fundamental building blocks of matter. From the primordial energy soup, particles and antiparticles flickered in and out of existence. Among the first particles to emerge were quarks and leptons, the fundamental constituents of matter. Quarks combined to form protons and neutrons, while leptons included familiar particles like electrons. The early universe was a chaotic soup of these fundamental particles, constantly colliding and interacting. As the universe continued to cool, a critical transition paved the way for the formation of the first elements. This was the early universe, a quantum dance floor where energy transformed into matter. It was from this chaotic yet creative environment that the universe as we know it began to take shape. The universe, still in its infancy, continued to cool, its temperature dropping to 1 billion degrees. This cooling allowed the fundamental particles to combine and form the first atomic nuclei. Protons and neutrons began to clump together under the influence of the strong nuclear force. This force overcame the electromagnetic repulsion between protons, allowing them to fuse and form helium. Along with helium, trace amounts of lithium and beryllium were also created. These first few minutes after the Big Bang were a time of incredible fertility, a cosmic nursery where the seeds of future stars and galaxies were sown. However, the universe was still too hot for electrons to be captured by these newly formed nuclei. This early period of nucleosynthesis played a crucial role in shaping the chemical composition of the universe. As the universe continued to expand and cool, a profound transformation occurred, the formation of the cosmic microwave background, or CMB. This faint afterglow of the Big Bang provides us with a snapshot of the universe as it existed 380,000 years after its birth. Before the CMB was released, the universe was a hot, dense plasma, a sea of charged particles. As the universe cooled, electrons combined with atomic nuclei, forming neutral atoms. With the formation of neutral atoms, the universe became transparent, allowing photons to travel freely. This release of radiation is what we observe today as the CMB. The CMB contains subtle temperature fluctuations, tiny ripples that reflect the density variations present in the early universe. These fluctuations would eventually grow into the stars, galaxies, and galaxy clusters we observe today. The universe, now cool enough for neutral atoms to exist, entered a new era of cosmic construction. The subtle density fluctuations in the early universe acted as gravitational seeds, pulling in surrounding matter. These clumps of matter, mostly hydrogen and helium, continued to coalesce under gravity's pull. As they contracted, they spun faster, eventually igniting nuclear fusion in their cores. Thus, the first stars were born, colossal balls of plasma, fusing hydrogen into helium. These early stars ionized the surrounding hydrogen, transforming the universe back into a plasma. As stars ignited and burned, they clustered together, forming the first galaxies. These early galaxies were the building blocks of the large-scale structure we see around us. For centuries, astronomers believed in a static, unchanging universe. However, in the early 20th century, observations revealed a universe far more dynamic. The universe was expanding, its very fabric stretching and carrying galaxies along. The first hints of this expansion came from Vesto Slipher, who noticed that the light from distant galaxies appeared redshifted. Edwin Hubble, using the Hooker telescope, discovered that the farther away a galaxy was, the faster it appeared to be moving away. This relationship, now known as Hubble's law, provided the first evidence for an expanding universe. Hubble's discovery transformed our view of a static universe into one that is dynamic and evolving. It also raised profound questions about the ultimate fate of the universe. As astronomers delved deeper into cosmic expansion, they discovered dark matter and dark energy. Dark matter, a mysterious substance, doesn't interact with light, but exerts gravitational effects on visible matter. Dark energy, an enigmatic force, pushes galaxies apart and accelerates the universe's expansion. Its existence was inferred from observations of distant supernovae, suggesting that the expansion was speeding up. Dark matter and dark energy make up the vast majority of the universe's energy density. Their existence challenges our understanding of fundamental physics, hinting at new particles and forces. The quest to unravel these mysteries drives the development of new telescopes, experiments, and models. By studying these entities, we hope to gain a deeper understanding of the universe's composition and evolution. The discovery of cosmic expansion and the mysteries of dark matter and dark energy have sparked speculation about the universe's fate. Current observations suggest that the universe's expansion is accelerating, driven by dark energy. If this acceleration continues, the universe will expand forever, becoming increasingly cold and dark. In this scenario, known as the Big Freeze, stars will exhaust their nuclear fuel and die out. Black holes will continue to grow, consuming any matter that ventures too close. However, the universe's ultimate fate is still uncertain. The nature of dark energy remains shrouded in mystery, potentially altering the universe's destiny. By studying the universe's expansion and probing dark matter and dark energy, we hope to understand the cosmos's grand narrative. As we contemplate the vastness of the cosmos, it's humbling to reflect on our place in this grand narrative. We are children of the stars, our existence intertwined with the universe's evolution. The atoms that make up our bodies were forged in the hearts of stars and scattered across the cosmos. Our planet is one of billions orbiting billions of stars in billions of galaxies. The study of the universe is a journey of self-discovery, revealing the interconnectedness of all things. We are part of a cosmic story that began billions of years ago and will continue to unfold. As we explore the cosmos, we do so with wonder, curiosity, and humility. The universe is a vast and mysterious place, full of beauty, complexity, and endless possibilities.
Look up at the night sky. Away from city lights, a faint band of light stretches across the cosmos. This is the Milky Way, our galactic home. But the Milky Way isn't alone. Spot a fuzzy patch of light, Andromeda, another spiral galaxy. Both galaxies are engaged in a cosmic ballet, drawn together by gravity. These two galaxies are on a collision course. When it happens, it will reshape our cosmic neighborhood. So buckle up, space cadets, for a thrilling ride through the cosmos.
Let's start with what we know, our own cosmic home, the Milky Way. Picture a flat disk with spiraling arms like a cosmic pinwheel. That's the Milky Way. It's a barred spiral galaxy, meaning it has a bar-shaped structure in its center. The Milky Way is about 100,000 light-years across. Our Sun resides in one of these spiral arms about 26,000 light-years from the center. The Milky Way is home to hundreds of billions of stars. New stars are born in vast clouds of gas and dust, while old stars die in spectacular supernova explosions. The Milky Way is our galactic home, a place of wonder and beauty.
Now let's journey beyond the Milky Way to our galactic neighbor, Andromeda. Located about 2.5 million light-years away, Andromeda is the closest major galaxy to us. Like the Milky Way, Andromeda is a spiral galaxy, but it's considerably larger, with a diameter of about 220,000 light-years. Andromeda has over 1 trillion stars. That's more than twice the number of stars in our Milky Way. It also has a massive black hole at its center, much larger than the one lurking in the heart of our galaxy. Andromeda is a fascinating object to observe. Its spiral arms are dotted with star-forming regions, glowing with the light of newborn stars. One of the most intriguing features of Andromeda is its double nucleus, 2 bright points of light at its center. Astronomers believe this double nucleus is the result of a past galactic merger, where Andromeda devoured a smaller galaxy. This gives us a glimpse of what's to come when Andromeda and the Milky Way eventually meet.
In the vast expanse of space, galaxies are not stationary objects. They move, they interact, they dance under the influence of gravity. And gravity, as we know it, is a powerful force, especially when it comes to massive objects like galaxies. The Milky Way and Andromeda are no exception to this cosmic dance. In fact, they're on a collision course, drawn together by their mutual gravitational attraction. You might think that galaxies colliding would be a catastrophic event, a cosmic demolition derby. But in reality, galactic collisions are more like graceful waltzes, albeit slow and drawn-out ones, spanning billions of years. The space between stars is vast, so individual stars are unlikely to collide during a galactic merger. Instead, the galaxies will pass through each other, their gravitational forces distorting their shapes, pulling out long streams of stars and gas, creating stunning cosmic displays. This gravitational interaction will eventually cause the 2 galaxies to merge, forming a single larger galaxy.
Section 5. A Dance of Titans, the collision course. The collision between the Milky Way and Andromeda is not something that will happen overnight. It's a slow-motion event, unfolding over billions of years. Astronomers estimate that the 2 galaxies are currently approaching each other at a speed of about 70 miles per second. At this rate, the collision is expected to begin in about 4 billion years. The first stage of the collision will be a close encounter. The 2 galaxies will pass through each other, their gravitational forces causing tidal tails of stars and gas to be pulled out from each galaxy. This encounter will disrupt the spiral structures of both galaxies, warping their shapes. Over the next few billion years, the Milky Way and Andromeda will continue to interact, passing through each other multiple times. Each encounter will further distort the galaxies, pulling out more stars and gas, creating a chaotic but beautiful cosmic display. Finally, after this cosmic dance, the 2 galaxies will merge completely, forming a new, larger elliptical galaxy.
Section 6. Star. Birth and Chaos. A cosmic ballet. During the collision, the galaxies won't just pass through each other without consequence. The gravitational interaction will stir up the gas and dust within each galaxy, triggering a frenzy of star formation. Imagine vast clouds of gas and dust, compressed by the gravitational forces of the colliding galaxies, igniting into a firestorm of star birth. New stars will blaze into existence, lighting up the cosmos with their brilliance. This period of intense star formation will be a spectacular sight, with new stars of all sizes and colors illuminating the merging galaxies. However, the collision won't be all about creation. Some stars will be flung out of the merging galaxies altogether, cast adrift into the vast emptiness of intergalactic space. Others will be drawn towards the center of the merging galaxies, where they will face a more chaotic fate.
Section 7. When galaxies collide, a new galactic order. As the Milky Way and Andromeda merge, their central supermassive black holes will also spiral towards each other, eventually merging into a single, even more massive black hole. This process will release tremendous amounts of energy, creating powerful jets of radiation that could be visible across the universe. The formation of this new galactic center will be a tumultuous event, with stars and gas swirling around the merging black holes at incredible speeds. The intense gravitational forces near the black hole will tear apart some stars, while others will be flung out into the surrounding galaxy. After billions of years of chaos and transformation, a new galactic order will emerge. The Milky Way and Andromeda will have combined to form a giant elliptical galaxy, a massive ball of stars with little gas and dust, much different from the spiral galaxies that preceded it.
Section 8. Milkomeda, the future of our cosmic neighborhood. This new galaxy, often nicknamed Milkomeda, will be a truly impressive sight. It will be a giant elliptical galaxy, much larger and brighter than either the Milky Way or Andromeda. The Sun, our star, will still be around, but its position in the new galaxy will be different. It might be flung further out into the galactic suburbs, or it might find itself closer to the center of the action. One thing is for sure, though. The night sky from Earth will be dramatically different. Instead of the familiar band of the Milky Way, we would see a bright, oval-shaped galaxy, a beacon of starlight in the cosmos. Milkomeda will be the dominant galaxy in our local group, a collection of over 50 galaxies gravitationally bound together. This merger will reshape our cosmic neighborhood, but it won't be the end of the story. The universe is constantly evolving, and new chapters are always being written in the grand cosmic narrative.
Section 9. A cosmic spectacle, billions of years in the making. The collision of the Milky Way and Andromeda is a reminder of the vast scales of time and space that govern our universe. These events unfold over billions of years, a timescale that dwarfs human comprehension. It's a humbling thought, but it also fills us with awe and wonder. We are fortunate to live in a time when we can witness these cosmic events, even if it's from a safe distance of millions of light years. We have powerful telescopes that allow us to study these galaxies in detail, unraveling the secrets of their formation and evolution. And we have computer simulations that can model these collisions, giving us a glimpse into the future of our own galaxy.
Section 10. Beyond the collision. The universe keeps expanding. While the Milky Way and Andromeda are destined to merge, the wider universe is expanding and the space between galaxies is increasing. This means that most galaxies are moving away from each other. However, some galaxies are close enough to each other that their gravitational attraction overcomes the expansion of the universe, leading to collisions and mergers. These galactic mergers are essential for the evolution of galaxies and the universe as a whole. They drive the formation of new stars, they reshape galaxies, and they create the diverse structures we see in the universe today. The universe is a dynamic and ever-changing place, and we are just beginning to understand the complex processes that govern its evolution.
Section 11. Keep looking up. The cosmos beckons. So, the next time you find yourself under a dark, starry sky, take a moment to appreciate the cosmic dance happening above you. The Milky Way, our galactic home, is on a collision course with Andromeda, our nearest galactic neighbor. But don't worry, this collision is billions of years in the making, and it promises to be a spectacular event, reshaping our cosmic neighborhood and creating a new giant elliptical galaxy. The universe is full of wonders, and we are constantly making new discoveries that challenge our understanding of the cosmos. So, keep looking up, keep asking questions, and keep exploring the vast unknown. The universe is out there, waiting to be discovered.
Our story begins with a giant cloud of gas and dust. This isn't just any ordinary cloud, but a massive, sprawling nebula that stretches across the vast expanse of space. Imagine a place where the light from distant stars barely penetrates, casting an ethereal glow on the swirling gases and dust particles. Imagine a cloud so big it could hold thousands of suns. This colossal cloud, known as a molecular cloud, is the birthplace of stars and planets. Within its depths, countless particles of gas and dust float aimlessly, waiting for the right conditions to spark the creation of new celestial bodies. This cloud was cold and dark, drifting through space. Temperatures within these clouds can plummet to just a few degrees above absolute zero, making them some of the coldest places in the universe. Despite the frigid conditions, these clouds are teeming with potential, holding the raw materials needed to create stars, planets, and even life itself. But something happened that changed everything. A dramatic event like a supernova explosion can send shockwaves rippling through the cloud. These shockwaves compress the gas and dust, triggering the process of star formation. Alternatively, the gravitational pull from a nearby passing star or another molecular cloud could disturb the delicate balance within the cloud. Maybe a star exploded nearby, or maybe a giant cloud bumped into our cloud. These cosmic collisions and explosions are not uncommon in the universe and play a crucial role in the life cycle of stars. The energy released from such events can be immense, enough to set off a chain reaction that leads to the birth of new stars. Whatever the cause, the cloud started to collapse in on itself. As gravity took hold, the once diffuse cloud began to condense, pulling the gas and dust particles closer together. This process, known as gravitational collapse, is the first step in the formation of a new star system. As the cloud collapsed, it got hotter and started to spin faster and faster. The conservation of angular momentum caused the cloud to flatten into a spinning disk, with the central region becoming increasingly dense and hot. This central core would eventually ignite to form a new star, while the surrounding material would coalesce to form planets, moons, and other celestial objects. This spinning cloud is where our solar system was born. Over millions of years, the particles within the disk collided and stuck together, gradually building up into larger and larger bodies. These planetesimals would continue to grow, eventually forming the planets, moons, and other objects that make up our solar system today. Scientists call this the nebula hypothesis. This theory provides a comprehensive explanation for the formation of our solar system, from the initial collapse of the molecular cloud to the development of the sun and planets. It is supported by a wealth of observational evidence and computer simulations, making it the most widely accepted model for solar system formation. It's the best explanation we have for how our sun, planets, and everything else came to be. By studying the nebula hypothesis, scientists can gain insights into the processes that shape not only our solar system, but also the countless other star systems scattered throughout the universe. This understanding helps us appreciate the complex and dynamic nature of the cosmos and our place within it.
At the center of the spinning cloud, things were getting really hot. The gas and dust were squeezed together so tightly that atoms began to fuse. This fusion released enormous amounts of energy. Boom! Our sun was born. The sun's powerful gravity kept pulling in more and more gas and dust. It grew bigger and brighter, eventually becoming the star we know and love today.
While the sun was forming, the rest of the cloud was still spinning. The spinning cloud flattened out into a disk around the sun. We call this the protoplanetary disk. It's where the planets formed. Inside this disk, tiny particles of dust and ice were bumping into each other. Over millions of years, these particles stuck together, growing bigger and bigger. They formed larger and larger objects, planetesimals, then protoplanets, and finally, planets.
Not all planets are the same. Close to the sun where it was hot, only rocky materials could survive. These materials came together to form the inner, rocky planets, Mercury, Venus, Earth, and Mars. Farther away from the sun, it was much colder. Here, huge amounts of gas and ice could also clump together. These formed the outer gas giant planets, Jupiter, Saturn, Uranus, and Neptune.
Section 5. Moons, asteroids, and comets. The solar system is more than just planets and the sun. It is a vast and dynamic place, filled with a variety of celestial bodies that each play a unique role in the cosmic dance. Beyond the 8 major planets and the central star, the Sun, there are countless other objects that contribute to the complexity and beauty of our solar system. It's also full of moons, asteroids, and comets. These objects, though smaller than planets, have fascinating characteristics and histories that make them worthy of study. They provide clues about the formation and evolution of the solar system. Moons are like smaller planets that orbit the larger planets. They come in various sizes and compositions, from rocky bodies to icy worlds. Some moons have atmospheres, volcanic activity, or even subsurface oceans, making them intriguing targets for exploration. Some planets have many moons, like Jupiter, which boasts 79 known moons, including the 4 large Galilean moons, Io, Europa, Ganymede, and Callisto. Each of these moons has unique features, such as Io's intense volcanic activity and Europa's potential subsurface ocean, while others have only a few or none at all. For instance, Mars has 2 small moons, Phobos and Deimos, while Earth has just one, our familiar moon, which has been a source of wonder and inspiration for humanity for millennia. Asteroids are rocky bodies that orbit the Sun. They are remnants from the early solar system, providing a glimpse into the building blocks of planets. Most asteroids are found in the asteroid belt between Mars and Jupiter, but they can also be found throughout the solar system. They are much smaller than planets and are often called minor planets. Some asteroids are rich in metals, while others are composed of carbon-rich materials. Studying asteroids can help us understand the conditions of the early solar system and the processes that led to the formation of planets. Comets are icy bodies that also orbit the Sun. They are often described as dirty snowballs because they are composed of ice, dust, and rocky material. Comets originate from the outer regions of the solar system, such as the Kuiper Belt and the Oort cloud. When they get close to the Sun, their ice vaporizes, creating a beautiful tail. This tail always points away from the Sun due to the solar wind. The study of comets can provide insights into the early solar system and the origins of water and organic molecules on Earth.
Section 6. The Asteroid Belt and the Kuiper Belt. In this section, we will explore 2 fascinating regions of our solar system that are teeming with celestial objects. Most of the asteroids in our solar system are found in a region between Mars and Jupiter called the Asteroid Belt. This vast expanse is home to millions of asteroids, ranging in size from tiny pebbles to massive rocks that are hundreds of kilometers in diameter. Think of it like a giant cosmic highway with millions of rocky travelers. These asteroids are remnants from the early solar system, offering us clues about its formation and evolution. They orbit the Sun in a relatively stable manner, creating a bustling yet orderly celestial neighborhood. Beyond Neptune, there's another region called the Kuiper Belt. This distant area is even more intriguing, as it stretches from the orbit of Neptune at about 30 astronomical units, AU, to approximately 55 AU from the Sun. It's like the asteroid belt, but much larger and made up mostly of icy objects instead of rocky ones. These icy bodies, known as Kuiper Belt objects, KBOs, include dwarf planets, comets, and other small solar system bodies. The Kuiper Belt is a treasure trove of information about the outer solar system. Pluto, which was once considered the 9th planet, is located in the Kuiper Belt. This dwarf planet, along with its moons, provides valuable insights into the characteristics and dynamics of KBOs. The discovery of Pluto and other similar objects has revolutionized our understanding of the solar system's architecture. The Kuiper Belt is also the source of many short-period comets, which have orbits that bring them close to the Sun more frequently than their long-period counterparts from the distant Oort cloud. These comets, with their spectacular tails, are a reminder of the dynamic and ever-changing nature of our solar system. Space missions, such as NASA's New Horizons, have provided us with unprecedented views and data from these distant regions. By studying the asteroid belt and the Kuiper belt, scientists hope to unlock the secrets of our solar system's past and gain a better understanding of its future. Both the asteroid belt and the Kuiper belt are essential components of our solar system, each offering unique insights into the building blocks of planets and the processes that shaped our cosmic neighborhood. As we continue to explore these regions, we are sure to uncover even more wonders and mysteries of the universe.
Section 7. Earth. The Goldilocks planet, our planet Earth, is a very special place. It orbits the Sun in a region called the Goldilocks zone. This means Earth is just the right distance from the Sun, not too hot and not too cold. This just right temperature allows liquid water to exist on Earth's surface. Liquid water is essential for life as we know it.
Section 8. Life in the solar system. As far as we know, Earth is the only place in our solar system with life, but scientists are searching for signs of life on other worlds, like Mars and some of Jupiter's and Saturn's moons. The discovery of life beyond Earth would be one of the most significant discoveries in human history. It would change our understanding of our place in the universe.
Section 9. The story continues. The formation of our solar system is an amazing story, full of cosmic collisions, swirling clouds, and the birth of stars and planets. And this is just the beginning. The solar system is constantly changing and evolving. Asteroids collide, comets streak through the darkness, and planets continue their dance around the sun.
Section 10. Our cosmic address. We live on a planet orbiting a star in a galaxy full of stars. And our galaxy is just one of billions of galaxies in the universe. The universe is vast and mysterious, and there's still so much we don't know. But by studying our own solar system, we can learn more about the universe around us and our place within it. Our cosmic journey is just beginning.
Hey everyone, today I'm going to take you on a journey that's going to blow your mind. We're diving deep into the multiverse theory. Ever wondered if our universe is just one of many? Well, buckle up. So what exactly is the multiverse? Imagine our universe as a bubble. Now imagine countless other bubbles floating around it. Each bubble represents a different universe. Some might be similar to ours, while others could be incredibly different. This idea isn't just science fiction. It's actually rooted in serious scientific theories. One of the most popular theories supporting the multiverse concept is cosmic inflation. Right after the Big Bang, the universe expanded rapidly in a process called inflation. Some scientists believe that this inflation didn't just happen in our universe, but in many others as well. These other universes could have formed their own unique bubbles, each with different physical constants and laws of nature. Fascinating, right? Now let's talk about quantum mechanics. According to the many worlds interpretation, every time a quantum event occurs, the universe splits into multiple distinct branches. In other words, there could be an infinite number of parallel universes, where every possible outcome of every decision ever made actually happens. Mind-blowing, isn't it? But what are the implications of the multiverse theory for our own universe? For one, it gives scientists a potential explanation for why our universe has the specific conditions that allow life to exist. If there are countless universes, each with different properties, it's not surprising that at least one, ours, would have the right conditions for life. This idea is known as the anthropic principle. Moreover, the multiverse theory challenges our understanding of reality. If other universes exist, could we ever communicate with them? Could we even travel between them? Scientists are still grappling with these questions, but the possibilities are endless and exhilarating. However, it's important to note that the multiverse remains a theory. As of now, we don't have any direct evidence to prove its existence. It's a tantalizing idea, but one that still requires much more research and exploration. So, what do you think? Are we just one of many universes in an infinite multiverse? The concept might be hard to wrap your head around, but it opens up a world, or should I say, worlds, of possibilities. If you found this video as fascinating as I did, make sure to like, share, and subscribe. Stay curious and keep looking up at the stars. Thanks for watching, and I'll see you in the next episode.